Okay, we're continuing with Chapter 2. Chapter 2 is about atoms, molecules, and ions. So what are atoms, molecules, and ions? Okay, but this chapter starts with sort of a brief history lesson, a two-part history lesson. So the first part was about atomic theory, how atomic theory was developed, the theory of matter, that matter is made up of these very small building blocks. That's what we talked about in the previous video. In this video, we're going to go through the second part of this history lesson, which talks about, so going into the 19th century, going into the 1800s, atomic theory gained traction and was becoming more universally accepted based on the experimental evidence that we talked about in the previous video. Okay, and so naturally, the next step was to ask questions about what exactly are atoms? Can atoms be subdivided into even smaller particles? Why do atoms behave the way they behave? Okay, so the structure of the atom. On the basis of Dalton's atomic theory, we can define an atom as the basic unit of an element that can enter into chemical combination. Okay, so this definition of an atom, it says the basic unit of an element. An element was defined in Chapter 1. Okay, an element is any substance that's composed of just one type of material, one type of atom. It doesn't mean that you can't have something like O2 or H2 or P8. So these molecules with multiple atoms in one molecule, that's fine. As long as it's just one type of atom, that's called an element, right? So again, P8 is an element. H2 is an element, the element hydrogen, oxygen, or just a single element, iron, a single atom element, right? Any of these substances are considered elements. And so the basic unit of an element that can enter into chemical combination is an atom, right? So you have H2 molecules, but one of those basic units here of these two-part molecules is a hydrogen atom. And what Dalton's saying is that can enter into chemical combination. What he's thinking about, you can imagine, is when he's making all of his hypotheses based on the chemical reactions they're experimenting with, they're recognizing that these building blocks are just rearranging themselves, going into different combinations in different simple proportions. And so these basic units that are just rearranging themselves, that they're seeing that the mass is conserved in these chemical reactions. It's always one part of this building block to three parts of this building block. He's calling that an atom. Whatever it is in these chemical reactions that they're experimenting with, and they divide the masses of like carbon consumed, hydrogen consumed, and they're getting these simple integers. Whatever is the basic unit that's resulting in these integer ratios, whatever it is that's rearranging itself when you go from, like a carbon monoxide type substance to a carbon dioxide type substance, he's calling that an atom. Okay, now, but it says Dalton imagined an atom that was both extremely small and indivisible, right? And why might he imagine this? Well, think about the masses. At the time, we know that they could measure the masses of these elements. They were incredibly small masses. So you might make a hypothesis that the atom was indivisible. It was so small. How could it be divisible? You can't even come close to seeing it with your eyes, right? But yeah, that is a good example of a hypothesis. We talked about hypotheses and theories and laws, etc. That would be a hypothesis. Dalton kind of imagined an atom that was both extremely small and indivisible. It can't become this couldn't become a theory until it's tested further. But it didn't become a theory because when it was further investigated, it was this hypothesis here by Dalton was disproved, obviously. That's what we're about to talk about. So, however, a series of investigations that began in the 1850s and extended into the 20th century clearly demonstrated that atoms actually possess internal structure. That is, they are made up of even smaller particles, which are called subatomic particles. This research led to the discovery of 3 such particles: electrons, protons, and neutrons. Okay, so first was the discovery of the electron. So in the 1890s, many scientists became caught up in the study of radiation, the emission and transmission of energy through space in the form of waves. Yeah, so with light coming from the sun, for example, or from like red hot material, there's this light and even heat that comes from matter. That's something else that they were curious about. What is this? What exactly is light? What exactly is heat? Heat that permeates through space. That they could tell it was energy. You know, you could get burned by hot radiation, but they were also concluding that they were dealing with waves, because you look at light, and actually in some sense it does seem to behave sort of like a ray. You can see light rays. It's like these particle rays, but in another sense it is like a wave. I mean, light spreads out. And then, in fact, we know when they were able to analyze light further, they would find a wave property, this propagating a electric and magnetic field in the form of a wave. So literally, you can measure it. It's got a wavelength, a frequency, a speed. But it's confusing, though. It is confusing. That's why they're trying to study it. Isaac Newton described light as more of like a ray, which, again, you do see light rays. It almost looks like these lines of light. But then again, we know you turn a light on in another room, and it'll spread out everywhere like a wave. So it is confusing, and then that's what they're trying to study it. So in the process of studying radiation, they were able to at the same time make great contributions to our understanding of atomic structure. One device used to investigate this phenomena was a cathode ray tube, the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the 2 metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, it produces a strong fluorescence or bright light. Okay, so here's a cathode ray tube. You've got this, it's a glass tube that's to where most of the air has been evacuated inside. They pull a vacuum inside. Okay, then you've got these 2 metal plates here with a high voltage applied between them. You have the negatively charged plate, which is, you can think about there's electrons here, and called the cathode, with a positively charged plate called the anode. The anode's got a hole in the center here. Okay, now, but as a result of the vacuum, in combination, you have the high voltage in combination with the vacuum, allows this phenomena to take place. Something goes from the cathode, is attracted to the anode, and then passes through this hole and continues to this coated surface here, where it produces this fluorescence, or this bright light. So even though they couldn't see the ray, they knew something was there because of the detecting screen. Okay, now it says, in some experiments, 2 electrically charged plates in a magnet were added to the outside of the cathode ray tube. When the magnetic field is on and the electric field is off, the cathode ray strikes point A. When the electric field is on, the ray strikes point C. When both the magnetic and the electric fields are off, or when they are both on but balanced so that they cancel each other's influence, the ray strikes point B. According to electromagnetic theory, a moving charged body behaves like a magnet and can interact with electric and magnetic fields through which it passes. Because the cathode ray is attracted by the plate bearing positive charges and repelled by the plate bearing negative charges, it must consist of negatively charged particles. We know these negatively charged particles as electrons. Okay, so they added electrically charged plates and a magnet to the outside of the cathode ray tube in this middle portion here where this invisible ray was traveling towards the detecting screen. Okay, and just by playing with the charge on the plates and the strength of the magnet, they were able to deflect this invisible ray. But they were able to do this in a way that was in conjunction with what they understood about electric charge at the time. They already had principles based on larger objects that showed that if you have a mass that has a positive charge on it, it's attracted to another mass with a negative charge on it, and then repelled if they're the same charge, etc. So this invisible ray here was acting like a charged material, a charged mass, right? You can imagine that this would not happen with something like radiation, like light. If they passed a light ray through here and played with the magnet and the charged plates, it wouldn't deflect the light ray, or even like some sort of a heat ray, heat radiation. Maybe they could have a thermally sensitive detecting screen here and see if you get a higher concentration of heat at different spots depending on how you charge the plates or intensify the magnet. No, they couldn't deflect radiation, but they could deflect this invisible ray here coming from these charged plates. Okay, and then you can think about they were also able to conclude that whatever was in these invisible rays was both lighter and smaller than measurements that they were taking as far as atomic weight and size. And so they knew that whatever this particle was, this mass, it was smaller than the atom, right? So, and hence subatomic particles. And then based on the way it was deflected by the magnet and the charged plates, they also knew that these particles were, whatever the particles were in these invisible rays, was negatively charged. Okay, so that's how the electron was discovered. Okay, figure 2.4 shows the effect of a bar magnet on the cathode ray. Okay, so here they create a cathode ray. You have this evacuated cylinder here with most of the air removed. There's a vacuum pulled, two charged plates. You put a high enough voltage between the plates, and then you'll get that, with the vacuum, you'll get that cathode ray. Okay, now it says the ray itself is invisible, but they used a trick here. They put a zinc sulfide coating on the glass, so it causes the ray to appear green. Okay, now it says the cathode ray is bent downward when a bar magnet is brought towards it, and then when the polarity of the magnet is reversed, the ray bends in the opposite direction. So yeah, this is just interesting. You can visibly see the cathode ray deflecting. And they knew that it was only masses that were deflected by magnets and electric fields, magnetic and electric fields. And they also had a sense for this cathode ray must have negatively charged particles in it because of the direction in which the ray was bending relative to the magnet. Okay, so now it says here electrons are normally associated with atoms. However, we can see here that you can study electrons individually, right? You got the charged plates where the electrons are contained. They're surrounding the atoms when they're contained within the metal plates. But then once you apply the voltage and the vacuum and you get the cathode ray, it's not like that. We know that the atoms don't come out of the metal with the electrons into the cathode ray. It's just the electrons. Okay. An English physicist, J.J. Thomson, used a cathode ray tube and his knowledge of electromagnetic theory to determine the ratio of electric charge to the mass of an individual electron. Okay, so the number he came up with was minus 1.76 times 10 to the 8th coulombs per gram, right? So this electron, this particle they couldn't see in the cathode ray, it obviously had a charge to it. Charge meaning with electromagnetic theory, just a charge means that you're attracted or repelled by other charged particles. It's just this phenomena of things pulling towards each other and repelling one another, sort of magically, right? In a similar way to gravity, but obviously distinct from gravity. Okay, so what they were wondering is, what's the sort of extent of this pull? That's what coulombs are. It's just telling you it's like the force of gravity, right? A coulomb is just stating the extent to which you will pull an opposite charge or push a like charge away from you. Okay, so what is for an electron, what is the coulombs of charge on the electron divided by the mass of the electron? What's that ratio? Thomson was able to, he couldn't get the exact mass of the electron right away, but he was able to determine this ratio of the charge to mass of the electron, which is still very powerful. Okay, so thereafter, in a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. So yeah, that's now that you have a precise measurement of the charge of the electron and you have the charge to mass ratio, well then what do you have? You can determine the mass of the electron, right? Millikan's work proved that the charge on each electron was exactly the same. In his experiment, Millikan examined the motion of single tiny drops of oil that picked up static charge from ions in the air. He suspended the charged drops in air by applying an electric field and followed their motions through a microscope. So, okay, yeah, here's a schematic of Millikan's oil drop experiment, how he determined the charge on the electron. So you've got these two chambers here, all right, and then they call this atomizer. This would just create as fine of a mist of oil as possible, very fine mist. The oil would gradually settle, and some of the oil would pass through this hole here. So in this bottom chamber, you have a positively charged plate and a negatively charged plate. So you've got this electric field in here. Okay, some of these oil droplets, which you can imagine they're trying to make them as fine as possible, pass through this hole in the center of the positively charged plate into this bottom chamber. Okay, and then you had an X-ray source here. So at the time of this experiment, they were able to, they had discovered X-rays, that's radiation, electromagnetic radiation, and they were using these X-rays. So X-rays would be relatively high energy electromagnetic radiation, right? These X-rays were being used to produce a charge on the oil droplets. And then with a viewing microscope, he could analyze the motions of the particles. The droplets were charged. You had an electric field with known magnitude because you knew the voltage you were applying to the plates. And then you had gravity. Right? So with the viewing microscope, you could get the size of the oil droplets. You knew the density of the oil. And you could analyze the motion, the change in position with respect to time, to get a sense for the accelerations, the forces, which corresponded to the charge. Okay, so Millikan found the charge on the electron to be minus 1.6022 times 10 to the minus 19 coulombs. And so with this, you could use that charge to mass ratio to get the mass of the electron. 9.1 times 10 to the minus 28 grams. And so, yeah, this is an exceedingly small mass. Okay, so that's the history of the discovery of the electron and the electron's fundamental properties, the charge on the electron and the mass of the electron. In 1895, the German physicist Wilhelm Röntgen noticed that cathode rays caused glass and metals to emit very unusual rays. This highly energetic radiation penetrated matter, darkened covered photographic plates, and caused a variety of substances to fluoresce. Because these rays could not be deflected by a magnet, they could not contain charged particles as cathode rays do. Röntgen called them X-rays because their nature was not known. Okay, so what you can think about here is they were aware of electromagnetic radiation coming from the sun, coming from matter in the form of like heat. And maybe they were even somewhat aware of lower energy electromagnetic radiation, like radio waves. Okay, but we don't naturally have around us X-rays or gamma rays just flying all over the place. X-rays and gamma rays are associated with special circumstances. We create X-rays. X-rays are created in like X-ray guns. You've got this really, really high voltage electric current that's brought to an abrupt stop, like a violent stop. And then out comes X-rays. That this doesn't happen just naturally in typical circumstances. This is like a manufactured situation. It can't happen naturally. It's just not common and typical like light is, light radiation, heat radiation, etc. Okay, and so what they're saying is that you can think about they're playing with these electron cathode rays, and perhaps Röntgen applied a really more of a higher voltage than normal to the cathode ray, directed it into certain glasses or metals, and out would come this really high energy or relatively high energy radiation. It would penetrate matter. Other radiation doesn't necessarily do that, right? Light in general is not going to penetrate matter. Heat's not going to penetrate matter. Yeah, I mean, it could heat up something and then through conduction, the heat will travel. But in most circumstances, you don't, if you shine a heat lamp on a solid and you put your hand on the other side, you're not going to feel that radiation until the heat travels through the actual material. Right? But this newly discovered magnetic radiation was penetrating matter to a much larger extent than other radiation. It would darken photographic plates and cause a variety of substances to fluoresce. This is something that all of the other electromagnetic radiation they were familiar with didn't do. Okay, but now again, you could imagine they wanted to check to see, well, is this perhaps a particle, or do these rays contain particles? And so these rays weren't deflected by a magnet, so which is just like light and heat radiation. So they concluded there was at least no charged particles like cathode rays, and so they were called X-rays because their nature was not known. All right. So now, not long after Röntgen's discovery, Antoine Becquerel, a professor of physics in Paris, began to study the fluorescent properties of substances. Purely by accident, he found that exposing thickly wrapped photographic plates to a certain uranium compound caused them to darken, even without the stimulation of cathode rays. Like X-rays, the rays from the uranium compound were highly energetic and could not be deflected by a magnet. But they differed from X-rays because they arose spontaneously. One of Becquerel's students, Marie Curie, suggested the name radioactivity to describe the spontaneous emission of particles and or radiation. Since then, any element that spontaneously emits radiation is said to be radioactive. Okay, so the story that was just told here is that they discovered certain substances that they would just place them in certain circumstances next to these thickly wrapped photographic plates, and it would cause the plates to darken. So what they're saying here is that they mentioned with X-rays would cause certain photographic plates to darken, which was an indication of that how high energy they were, right? Well, now you've got these thickly wrapped photographic plates, and that were being darkened by just taking a material and just putting it in front of these wrapped plates. So what this is stating is that whatever is causing these photographic plates to darken is extremely high energy, more high energy than the X-rays, really high energy. But then it's also unique in that the X-rays were having to be generated by a current, a cathode ray. You had to generate the X-rays. These were just spontaneously just coming out of these materials, this uranium, right? That's what they mean here. Without the stimulation of cathode rays, they didn't need to do anything. This was just naturally happening. Okay, and then like X-rays, they saw that these rays couldn't be deflected by a magnet either. So it must be radiation. Okay, and so Marie Curie suggested the name radioactivity to describe this radiation that was being emitted spontaneously from these materials. All right, now it says emission of particles and or radiation because now we know that radioactivity is not just electromagnetic radiation. You've got gamma rays, which is electromagnetic radiation, but there also is there's particles being emitted as well. Okay, but you can imagine at the time during this discovery here, they didn't know that, and so that's where the name radioactivity comes from. They're assuming it's just this pure non-particle radiation being spontaneously emitted here. And so even after with more research, they discovered it wasn't just pure radiation. There was also particles. The name radioactivity still stuck. All right, but today we know that in reality, there's three types of rays are produced by what's called the decay or breakdown of these radioactive substances, such as uranium. It's the nucleus breaking down. That's why it's so high energy. It's not the electrons, it's the nucleus. Okay, two of the three are deflected by oppositely charged metal plates. So alpha rays, we know it's a clump of 2 protons and 2 neutrons. So it's positively charged, still extremely high energy. So this is not radiation, these are alpha particles. Okay, and then beta rays or beta particles are electrons, but they're still coming from the nucleus. We know there's no the nucleus doesn't contain electrons, just protons and neutrons, but it's a special case. I'm not going to go into the details here, but it's still extremely high energy electron streams. Okay, but then there's this third type of radioactive decay, which is electromagnetic radiation, the highest energy electromagnetic radiation that we're aware of, called gamma rays, which aren't charged, right? They're like any electromagnetic radiation, they're uncharged, not affected by an external electric or magnetic field. Okay, now the proton and the nucleus. By the early 1900s, two features of atoms had become clear. They contain electrons and they are electrically neutral. Okay, to maintain electric neutrality, an atom must contain an equal number of positive and negative charges. So yeah, you can think about how at the time that they could measure the mass of an atom, and we just saw they determined the mass of an electron. Okay, and we know that relative to the total mass of an atom, the mass of electrons are like thousands of times smaller. Okay, but you could potentially think that, oh, well, maybe it's the atom is made up of thousands or millions of electrons then, but at the same time, what they realized was that atoms in general are neutral. They're not deflected by magnetic or electric fields. So there's, at least to some extent, there's got to be some sort of positive charge within the atom that's neutralizing the charge of the electrons, for sure. Okay, so it says, therefore, Thomson proposed that an atom could be thought of as a uniform positive sphere of matter in which electrons are embedded like raisins in a cake. This so-called plum pudding model was the accepted theory for a number of years. So yeah, with this model, if you're going to assume that an atom has something like 7 or 8 or 20 electrons, well, then you're going to have to, with that, since that would mean that the electrons make up a really tiny percentage of the total mass of the atom, because again, they knew the mass of the atom, they knew the mass of the electron, then the mass of one electron is thousands of times smaller than the mass of the entire atom. Well, then you're going to have to conclude that that this would make sense. This sort of cake plum pudding model here, you've got all this positive charge, but that which offsets the charge of the electrons, but there's where all the mass of the atom is coming from, this pudding, right? And so that was the accepted theory for a number of years. Okay, in 1910, the New Zealand physicist Ernest Rutherford, who had studied with Thomson at Cambridge University, decided to use alpha particles to probe the structure of atoms. Okay, so alpha particles, the radioactivity, high energy alpha particles. Together with his associate Hans Geiger and an undergraduate named Ernest Marsden, Rutherford carried out a series of experiments using very thin foils of gold and other metals as targets for alpha particles from a radioactive source. Right, so you've got this alpha particle emitter here, radioactive source, which you can imagine is just like a piece of uranium or something, but with a fixture around it to maybe with a small tunnel to direct only certain alpha particles out. Okay, goes through this slit here. You've got this detecting screen to detect alpha particles, and then in the center is a thin gold or metal film. So that's the experiment. All right, so what did they observe? They observed that the majority of particles penetrated the foil either undeflected or with only a slight deflection, okay? But every now and then, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse that the positive alpha particles should have passed through the foil with very little deflection. To quote Rutherford's initial reaction when told of this discovery, it was as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Yeah, so what they're saying is with Rutherford's plum pudding model, to be in conjunction with the mass of the atom, you had this sort of more diffuse pudding, to where you can think about in at the beginning of this experiment, as the alpha particles were just passing straight through or being deflected slightly, this made sense. Because you had more of a thin kind of plum pudding, but then you were shooting these extremely high energy alpha particles. And so then when all of a sudden, every now and then, you had these alpha particles not just being deflected, but being deflected at extreme angles, and even almost it was like they were hitting a brick wall and coming straight back. That must have been shocking, because again, we know how the extent of the energy level of radioactive decay. Okay, and so with this discovery, it says Rutherford was later able to explain the results of the alpha scattering experiment in terms of a new model for the atom. According to Rutherford, most of the atom must be empty space. This explains why the majority of alpha particles passed through the gold foil with little or no deflection. The atom's positive charges of the alpha particles, right? They're positively charged, Rutherford proposed, are all concentrated in the nucleus, which is a dense central core within the atom. Whenever an alpha particle came close to a nucleus in the scattering experiment, it experienced a large repulsive force and therefore a large deflection. Moreover, an alpha particle tunneling directly towards a nucleus would be completely repelled and its direction would be reversed. That's amazing, right? Amazing when you consider what the highest energy phenomena that we know of today is like a nuclear bomb. And these alpha particles weren't just being deflected by the nucleus. It was like they were hitting a brick wall and then some. So you could hit a brick wall and stop, but it's not just hitting the brick wall, but the brick wall is actually throwing you back the other way. And so that's where the conclusion came, that's what we know of as the atom today. We think of it as mostly empty space, because electrons are really tiny, right? They're really small, lightweight. There's not thousands of electrons in atoms. There's a normal number. So the electrons make up a negligible percentage of the weight of the atom. So all of that weight of an atom is in the nucleus, which you can imagine they were able to get a sense of just how small the nucleus was by seeing, the percentage of these alpha particles that were deflected, which was probably a really low percentage. It was only in these special cases where you had alpha particles deflected extremely, because the atom was mostly empty space. And furthermore, the nucleus must have been incomprehensibly dense to do what it was doing to the alpha particles. That was also an indication that the nucleus must be, it's the atom is mostly empty space. You have this small nucleus with all of this mass contained in that small space, an extremely dense nucleus. As kind of incomprehensibly small atoms are, when we think about the whole, people will talk about, you could, the amount of atoms in your fingernail can extend to the, if you took that number of baseballs, you'd go to the moon and back 10 times. Those types of descriptions, like incomprehensible. It's the same idea as far as we'll talk about in a second, the how much empty space that the atom really is, and also how dense the nucleus is. It's incomprehensible. Yeah, so we'll talk about that in a second. It says that the positively charged particles in the nucleus are called protons. And so, yeah, we're going to talk about this in a little more detail in Chapter 8, but you can think about, they knew that the nucleus contained positive charge, but right away they might not have known what exactly that positive charge was. Was it like more pudding, like a dense pudding? Was it particles, right? So that required more investigation, but at some point they realized it was charged particles. Okay, in separate experiments, it was found that each proton carries the same quantity of charge as an electron and has a mass of, so on the order of 10 to the minus 24. The electron was 10 to the minus 28, about 1,840 times heavier than the electron. Okay, so the masses are different of the electron and the proton, but the charges are identical. Okay. At this stage of investigation, scientists perceived the atom as follows. The mass of a nucleus constitutes most of the mass of the entire atom, okay, but the nucleus occupies only about 1 over 10 to the 13th of the volume of the atom. That's insane. 1 over 10 to the 13th. We express atomic and molecular dimensions in terms of, so yeah, okay, a picometer is 10 to the minus 12. Okay, so this is like a 1 over, even a bit smaller than a picometer, which is, again, just incomprehensible, a fraction this small. To say that all of the mass of the atom is contained within this 1 over 10 to the 13th of the volume is just incomprehensible. Again, when I'm saying incomprehensible, I mean the sense of the whole, the atoms, the number of atoms in your fingernail, if you took that many baseballs, it would go around the Earth 20 times, just stuff like that. Okay, a typical atomic radius is about 100 picometers, whereas the radius of an atomic nucleus is only about 5 times 10 to the minus 3 picometers. You can appreciate the relative sizes of an atom and its nucleus by imagining that if an atom were the size of a sports stadium, the volume of its nucleus would be comparable to that of a small marble at the center. Although the protons are confined to the nucleus of the atom, the electrons are conceived of as being spread out about the nucleus at some distance from it. So yeah, that gives you the sense of how the atom is mostly empty space. You have a football stadium. At the center of the stadium is a marble. The marble is the nucleus. The stadium is the atom, all the electrons. And again, they're saying, we know that the electrons are a negligible amount of mass compared to the protons in the nucleus. So all of that mass, which would be like 99 point something percent of the mass, is in that marble. Okay, and then to think about the incomprehensibility of that density, right? Because they have a sense for the radius of the atomic nucleus, the volume of the atomic nucleus. They know the mass of the atom, so they could get a sense for the density of the nucleus. It's something like if you took the Earth, the entire mass of the Earth and shrunk it down to where you had a sphere that was 2 football fields in diameter, that would be the density of the nucleus. Just incomprehensible. Okay, now the neutron, the last subatomic particle, the last piece of the puzzle when it comes to our modern understanding of atomic structure, at least from the chemistry perspective. Yeah, you can get, and there's particles inside of protons, etc. But just for chemistry, the last piece of the puzzle here is the neutron. Okay, Rutherford's model of atomic structure left one major problem unsolved. It was known that hydrogen, the simplest atom, contains only 1 proton, and that the helium atom contains 2 protons. Therefore, the ratio of the mass of a helium atom to that of a hydrogen atom should be 2 to 1. Because electrons are much lighter than protons, their contribution to atomic mass can be ignored. Yeah, when calculating atomic masses, we don't, in typical calculations, we don't need the 5th, 6th, 7th decimal place, and that's what would come into play if we were factoring in the mass of electrons with atomic mass. In reality, however, the ratio is 4 to 1. So yeah, they had figured out that the number of protons in helium is 2 and in hydrogen is 1. And so they were expecting then, if the nucleus contains the entire mass of the atom with these protons, the ratio of the mass of helium to hydrogen should be 2 to 1. And just a reminder, the hydrogen atom doesn't have neutrons, which probably confused them a little bit in the beginning. There are isotopes of hydrogen that do contain neutrons, but in general, hydrogen doesn't have any neutrons. Okay, but what they were finding was that in reality, the ratio of the mass of helium to hydrogen was 4 to 1. Okay, so Rutherford and others postulated that there must be another type of subatomic particle in the atomic nucleus. The proof was provided by another English physicist, James Chadwick, in 1932. When Chadwick bombarded a thin sheet of beryllium with alpha particles, a very high-energy radiation similar to gamma rays was emitted by the metal. Later experiments showed that the rays actually consisted of a third type of subatomic particle, which Chadwick named neutrons, because they proved to be electrically neutral particles having a mass slightly greater than that of protons. The mystery of the mass ratio could now be explained. In the helium nucleus, there are 2 protons and 2 neutrons. But in the hydrogen nucleus, there is only 1 proton and no neutrons. Therefore, the ratio is of the masses is just 4 to 1. So yeah, you can think about how they were, to try to figure out what was going on here, you could bombard a nucleus with high energy gamma rays and see what happens. Try and maybe break up the nucleus or something. Okay, and what they found was that there was this unique type of energy emission that it was similar to gamma rays because it was uncharged. Okay, but they could see that it wasn't technically gamma rays, though. It was something else. And obviously it couldn't be alpha rays or beta rays because it wasn't charged. They discovered it was a particle, not a ray. And there you go. That's how they discovered these uncharged particles in coming out of the nucleus, neutrons. Right now it says the neutrons had a slightly greater mass than that of protons, but it's really slight. Okay, so it says this figure here shows the location of the elementary particles, protons, neutrons, and electrons in an atom. There are other subatomic particles, but the electron, proton, and neutron are the main ones that we're thinking about for general chemistry. But so you've got this tiny nucleus here, and then surrounded by an electron cloud. So most of the diagrams you see of an atom are not to scale. To make it more visually illustrative, they make the nucleus a lot larger relative to the electron cloud than it actually is. Right? Even this is probably not even drawn correctly to scale. We probably couldn't even visually see the nucleus. We shouldn't even put a dot here. Right? But in the nucleus, you've got protons and neutrons packed in most cases, except for the common hydrogen isotope, H1. right? But again, you have these protons and neutrons packed in here. And then, yeah, you can see so here's the mass of the proton and the neutron. They are technically different, but only by a very slight amount, right? 1.67262 times 10 to the minus 24, 1.67493 times 10 to the minus 24. Okay, with the electron being about, 2,000 times smaller, smaller in mass and radius as well, but actually it's not quite as extreme when it comes to the size. I believe the electron is only about 10 times smaller in volume, or at least in terms of the radiuses, than the proton and the neutron, with the proton and neutron, like the mass, having similar radiuses or diameters. Okay, but the neutron is uncharged, and the electron and the proton have the exact same charge.